Today we are going to be solving this problem. It says determine the slope at B and the maximum displacement of the beam. Take E, is given E and I. For this problem, we are going to be using the method of double integration. Okay, there are other methods for solving it, but we are going to be choosing to use the method of double integration. First things, we need to find the reactions, and this is a fixed support beam, so we have all three reactions at this point. Here we have AY, we have AX, and we have the moment MA. Okay, so in order to find all three reactions here, it's pretty simple. We do the summation of the forces in the Y equal to 0. Going up is going to be positive, and for this case here we only have two forces, so we have AY and minus 15 kips, and this is equal to 0, is going to lead us to AY equal to 15 kips. So we have the first reaction. Now to the moment calculations, see here that the moment of inertia here is given in inches to the fourth, and this one is given in KSI, and here the distance is given foot. Okay, so I'm going to change it, and I'm going to get the distances in inches. So just multiply by 12 here, and then we have this distance is going to be 72 inches in this side, and also 72 inches in this side. So we don't need to be changing the units later on the problem. Now to find the moment MA, I have to take a moment about a specific point. I'm going to take the moment about point A. So we do the summation of the moment about point A is equal to 0. Going counterclockwise is going to be positive. And right here we only have the MA. And then this is going to be positive. And then we have the negative 15, which is going to be a negative moment, times the distance, which is 72. This is equal to 0, and this is going to lead us to a moment MA equal to, is going to be positive, right? When we change it, 1080, and this is going to be kips times inches. Okay, so we have the moment MA, we have AY, and obviously if you want to calculate it, I'm going to put here in the corner EX is going to be equal to 0 because we don't have any horizontal forces here. Now we need to find where we are going to place the x1 and x2 to get our calculations and to find the slopes using the method of double integration. So I'm going to define my x1 going here between point A and point B, and I'm going to define an x2 at point C that goes between C and B. Okay, so let's start with x1. For x1, we are going to place a cut somewhere here between A and B, and then when you place a cut, we have the moment, which is going to be here M1, and this moment M1, we also have the shear and axial force that I'm not going to draw because I'm not going to use it. So now if you want to calculate it, we just need to calculate this moment doing the summation of the moment about the cut. Okay, is equal to 0, counterclockwise is positive. So if you do it, we have M1, and then we have the distance x1 with respect to AY, and this is going to create a counterclockwise moment, so we have negative AY times the distance, which is x1, and we also have the MA, which is a positive moment, and MA we calculated here. I'm just going to write it MA first equal to 0, but then we know that MA is 1080, so we can replace it, and therefore we have that our M1 is going to be, let me just write here, we also have AY is equal to 15. Okay, so when we rearrange, we have 15 times x1, and then we have negative 1080, and this is going to be our moment M1. Okay, I'm going to take the opportunity here because I can draw later side by side. I'm going to do the cut for x2 as well, and then if I do the cut, if I have drawn my x2 going in the opposite direction like f1, I have to also change the way my cut works, and now the moment is going to be clockwise. In this case, I have my M2 right here. See this, my cut is basically this portion here that I'll be looking for, while for M1 was this portion here that I was looking for. And in this portion I have all the forces at the support, but here I have no force. So if I do sum of the moments about the cut 2 equal to 0, and this is going to be my sign, I only have M2 and nothing else. So therefore M2 is going to be 0. So our moment M2 is going to be equal to 0. See? So the location you select your x1 and x2 is going to be very important for the development of your problem. In this case, it's going to be very easy to work with this x2 right here because everything is going to be 0. Okay? So now we have to write the equations for the double integration method. And the equations is the following. We have EI, and then we have d2v over dx2 squared. Okay, and this is going to be equal to our moment varying with the x. So we can do calculations for both for M1 and M2 simultaneously. So we can do here for the first one, we have EI, we have d2v over dx. This is going to be this x1 squared, and our M1 is going to be 15 x1 minus 1080. And then if you take an integral, right, to get to the next level, we are going to take integral on both sides. And then when you take an integral here, we have EI, and then we have just dv1 over dx1 is going to be equal to this one. If you take an integral, we have 15 x1 squared over 2 minus 1080 x1 plus c1. And then if you take another integral, we have EI, we just have now v1 is equal to 15. Now it goes to the third, x1 to the third, and drops a 3. 3 times 2 is 6 minus 1080 x1 squared over 2 plus c1 x1 plus c2. Okay, so we have equation 1 and equation 2 that we are going to be using later on. Now I'm going to do a similar calculations, but for my moment 2. So we start off with our double integration equation, and we have here EI d2 now is v2 dx2 squared equal to our moment, which is 0. So if it's 0, we cannot do anything. But then when you take an integral, we still can. If you take an integral here, we are going to have EI d2 v2. Actually, we don't have the square. It's just dv2 dx2 is equal. If you take an integral, you're only going to add a constant, which is going to be c3. And then if you do an integral again, we have EI v2 is equal to not c2, it's going to be c3 x2 plus c4. So we have two more equations here. We have the third equation and the fourth. And now we need to find boundary conditions to solve this problem. The first one that's pretty clear to see is that the fixed support, the displacement and the rotation is going to be 0. And for those of you who don't remember, this dv1 here, it means rotation, okay? We also call theta. So this is rotation. So our first boundary conditions, and I'm gonna put here boundary conditions, we have that from our x1 equal to 0, I mean at the very beginning, so x1 equal to 0, our rotation theta 1 is equal to 0, and our displacement v1 is also equal to 0. So we can use this equation 1 and 2 here to find c1 and c2. Okay, so let's do it together. for this one, we have the first, which is going to be EI. The rotation for this is going to be dv1 over dx1 is equal to 15x1 squared over 2 minus 1080 x1 plus c1. If you make x1 equal to 0, this whole thing goes to 0. If you make x1 0 here, it goes to 0, and this, the rotation is 0, so everything goes to 0, and therefore we find that our c1 is equal to 0. So we have our first constant found. Now, for this one, we have used the first boundary condition, which is theta 1 equal to 0, meaning that I made this term goes to 0. Now we are going to use the second here equation, but this is going to use the displacement equal to 0, meaning this term here goes to 0. So we have EI V1 is equal to 15 x1 cubed over 6 minus 1080 x1 squared over 2 plus c1, but c1 is 0, so we don't put it, and then you have plus c2. Okay, so again, the x is going to be 0 for this condition, so if it's x is 0, and v1 is 0, and we only have c2, it's going to end up c2 is equal to 0. So we have found the first two constants, c1 and c2 is equal to 0. Now we have two more left, c3 and c4. And the way we are going to do to find those two is to use the continuity conditions now. And for the continuity condition, the deflection at this beam is going to be something like this is a beam that is a free end in the right side, and we only have the fixed support right here. So it's going to be something, let me use a dark color, I'm going to use the red. So the deflection is going to be something like this. Okay? Meaning this, although I have picked my x1 to go from the left to the right and x2 to the right to the left, at somewhere here at the midpoint, they are going to meet. And whenever they meet, they must have the same inclination, which means the same rotation and the same displacement, right? So if they must have the same displacement, now we have our third and fourth conditions, which is going to be the continuity conditions. And we have at the midpoint, okay, and means that x1 is going to be equal 72, and also x2 is going to be 72. So x1 equal to x2 equal to 72. It means that the rotation theta 1 has to be equal to theta negative theta 2, and the displacement theta 1 has to be equal to theta 2. And see this here, I have a negative sign because the rotation from one side and from the other side, like I had the drawing here, let me do again. If I had going to be something like this, okay, let me do it steeper. So it's going to be something like this. The rotation looking from this side is going to be something like this, but looking from this side is something like this, okay? We have the rotation here. And in order to those two rotations to match, one has to be flipped. And by flipping, I mean a negative sign. And that's the reason why we have to put a negative sign here, okay? So we just need to make equation 1 equal to equation 3, equation 2 equal to equation 4. So let's start with the first ones. So for equation 1, we have 15 x1 squared over 2 minus 1080 x1. C1 is going to be 0, so we ignore, and then we have equal to the second equation, to the third equation, which means C3. And so here we just need to replace x1 by the location 72 that we are looking at. So we have 72. And then here we just need to do this B calculation right here. And then if you do this calculation, we have C3 is going to be equal to 38,880, and this is in rotation units, which means it's in radians. So I'm gonna put rad. Now we are going to make equal the second and fourth equation. So we have 15 x1 squared over 6. Actually, it's not square, it's to the cube over 6. And then we have minus 1080 x1 squared over 2. And then we have C1 and C2, they are both 0, so we don't need to plug in here. And this is going to be equal to C3 times x2, and C3 no is 38,880 times x2, and then we have plus C4. So we go here plus C4. We can see this x1, they are going to be 72, right? We are looking at x1 equal to x2 equal to 72. X1 here is also 72. And then we have the x2 as well is going to be 72. So that's going to be just, a bunch of calculation here. I have already done it. And we have that C4 is going to be equal to negative 4665600, and the unit here is going to be inches. The only reason this is displacement is because we have assumed initially going up to be positive, so if it's going down it's going to be negative, and that's why here is going to be negative, right? So we have our third, which is C3, and the fourth equations. So if you look at here now, the problem says determine the slope at B and the maximum displacement of the beam. All right, like I said, the maximum displacement, if you look at the drawing, if you have a fixed point right here, the beam is going to deflect somewhere like this, where the maximum displacement is going to happen here. This is the maximum displacement. Okay, so the maximum is going to happen at point C, and for point C I have to use the x2, right, equations, because I'm using from this side. And in this case I'm going just to erase so it doesn't get too messy. For this case I'm just need to for the displacement equation, which is the fourth equation, I need to make at point C, which means my x2 is going to be 0. So I'm going to do here my maximum displacement is going to be delta, and for this one I'm going to use this equation. So I have EI V2, this is going to be equal to C3x2, and we have C3 here, so it's going to be 38,880 x2 plus C4, but C4 is negative, so we have negative 4665600. Like I mentioned, the displacement is going to happen at point C, which is this point, and meaning that for x2 is going to be 0. So x2 here is going to be 0. So this whole thing here goes to 0. And then we just need to plug in EI that we are given in the problem, 29 10 to the third and 500. And then we can find our maximum displacement. So we have V2 is going to be equal to negative 4665600 over the EI, which is 29 times 10 to the third times 500. And then if you do this calculation, you're going to find that V2 is going to be equal to 0.32 inches. Okay, I remove the negative sign because it doesn't matter, we are looking just the displacement. We know that the negative is because it's going down, so the displacement here is going to be 0.32 is going to be the maximum. Okay, and then also the problem asks the slope at B, and the slope at B, B is this point at midpoint. So I can either use the equation of 1 or the equation of x2, but the equation of x2 is much simpler, right? I only have this equation, so I'm going to use the equation 3 to find the slope. So is slope at B. For the slope at B, I have EI theta B in this case. So I have EI theta B is going to be equal to C3 is equal to C3, and C3 no is 38,880. So in order to find theta B, we just needed theta B is equal to 38,880 divided by the EI, which we have here is 29 times 10 to the third times 500. And this is going to tell us that theta B is equal to, if you do these calculations, it's going to be 2.68 times 10 to the negative 3. This is going to be in radians. Is if you just want to rewrite it to remove the exponent, we have theta B is equal to 0.00268 radians. Okay. So in this problem, we have used the method of double integration to find the elastic equations, and also we found the maximum displacement is 0.32 and the rotation at point B, which is 0.00268 radians. Okay, I hope I have helped. Try to redo this problem on your own and see the solution matches with mine. All right, thank you guys. I see you in the next video.